Alright, so we're on our second video for the chain rule. So basically what we're going to do is we're going to do a lot of practice of all the different things that you can see with the chain rule. Alright, so let's get started. Let's do a classic example. We want to find all points on the graph of f of x for which the derivative does not equal 0. So that would be the place where we have horizontal tangents. And then we're also going to look for the place for which the derivative does not exist, so all the values for which f of x is not differentiable. And the nice thing about this, especially now that we have shortcut rules, is that when we're trying to determine places where you're not differentiable, clearly you would be not differentiable if the original function is not continuous, and then we would also come up with our vertical tangent and our cusp that would happen on the original function. We will see that in the derivative by the fact that you basically have a division by zero problem, that the derivative would not exist because the derivative itself is discontinuous. So one of the things that I may kind of discuss here is we do want to talk about this function and determine whether or not that has any discontinuity. So I'd like to know whether f is continuous since I'm looking about where the derivative doesn't exist. In terms of continuity on this, basically what we're going to look at is the domain of this, and clearly this is a squared and a cube root and x squared minus 1. There's nothing that's going to be a division by 0 or an even root or anything that's going to cause us, or a log or something like that that's going to cause us. So this is defined everywhere. And so this is a continuous function. There's no discontinuities on this function. It's the composition of continuous functions. All right, so that's fairly straightforward. Let's kind of talk about that before we start. Now, step one that you're going to be looking at here is we want to take this function, we want to find the derivative. So step one, we want to find f prime of x, and clearly that's going to be a chain rule problem. It's actually a chain rule problem twice because we have a composition within a composition. So we have kind of three parts to this that we're going to do. All right. First thing, though, I'm going to make it so it's easier. Instead of doing a three-part chain rule, I'm going to realize that these are nothing more than a power and a power. So I'm going to rewrite my function f of x so that it's in a nicer form. So I don't have to do chain rule 3 times. That basically what I'm going to do is go, let's rewrite this as x squared minus 1 to the 2/3. And then that makes it into where I only have to do chain rule once. Okay, so now we're going to use chain rule. I'm going to let my u, my inside function, is going to be x squared minus 1. My du dx is going to be 2x. So I'm going to remember that kind of as we go through the process. And basically, we're going to take the derivative of u to the 2/3 when I'm doing my chain rule. That's y. So dy du would be 2/3 u to the negative 1/3. And so that, and then of course followed by u prime, which is going to come from over here. And so we're going to come in here and we're going to do our derivative. So I'm just going to go ahead and fill it in with the parts that I have. F prime of x is going to be this with u put back in. So 2/3 x squared minus 1 to the negative 1/3 times du dx, because I have dy du, and then if I take dy du times du dx, that's going to give me my dy dx that I'm looking for. All right, so we have our chain rule in. And now, at this point, because I need to use it to do something, I need to simplify. So step 2, after I find it, is simplify f prime of x into a nice form. I'll put that in quotation marks, which basically means factored if possible, one fraction if possible, something that it's easy to determine where it's equal to 0 and where it's undefined. Now for this, it's fairly straightforward. Negative exponents drop to the bottom. We'll put the top and put it into a single fraction. So we would have, it actually doesn't matter about the 2 and 2x. You can write 4x. That's perfectly fine. Our 3 and our x squared minus 1 to the 1/3 and put it down there. You can also kind of think of this as simply 4x, 3, and then cube root of x squared minus 1. Sometimes this is a preferable version since we're going to do something for that. Now the two parts of this problem are to figure out where you have horizontal tangents. So we'll do that first. Horizontal tangents are basically where our derivative is equal to 0. And again, why are we doing this? Because horizontal tangents are going to be possible extrema and also possible points of inflection if it kind of comes in, flattens out, and keeps going, or comes up and down. It kind of depends. We can determine later what it is, but right now we just want to know, can we find horizontal tangents? So we set our f prime of x equal to 0, so the work that you would show, take what you found, the nice form of our derivative, and we set that equal to 0. And what you want to go ahead and do is think about what your restrictions are, because remember that restrictions cannot be solutions when you set it equal to 0. The restrictions would be x equal to plus or minus 1. How is that going to be able to answer the question? That's the second part of this in a second very easily. But in a fraction, the part that matters when you are equal to 0 is the top. So we go 4x equal to 0 or x equal to 0. So at x equal to 0, our f prime of 0 is going to equal 0, and there is a horizontal tangent. Right? And so remember that basically what you're looking at, and this is why the fraction form is the nicest, if you get a number 0 over a number equal to 0, this is where we would have a horizontal tangent. That's what we're looking for in this. That's also why I checked to make sure I didn't get 0 over 0, because if that's true, then it's not a horizontal tangent, it's a discontinuity. And basically, now that I did this work over here, I can now pretty much straightforward answer the second question. The second question was determine when f prime of x does not exist, which basically means that what you're doing is you're looking for the discontinuities on f prime of x, that any place where the derivative is undefined is going to be a place where you are not differentiable. We don't have to worry about the what we were doing with the free response example that we had before, because it's not a piecewise function. This is just a generic function, so we can use the rule to help us find it. And a fraction is undefined when you get 0 over a number, or sorry, if you get a number over 0 or 0 over 0. So if f prime of x equals 0 over 0 or a number over 0, then you're going to have it's going to be discontinuous and it would be not differentiable there. It would not exist. So pretty much in the fraction, all I need to do is set the denominator equal to 0. So we would go 3 cube root of x squared minus 1 equal to 0, which is clearly going to equal 0 when x squared minus 1 equals 0 or x equals plus or minus 1. So this would be the location of everywhere where you have a part of the function. Now since, okay, kind of talking about this, now since this is a place where the function is not differentiable, let's talk about what this means. What we know now, and also since I already had the conversation that f was continuous everywhere, so it's continuous at x equal to plus or minus 1, so what is happening on the function at plus or minus 1, it must have either a cusp or a vertical tangent where you have your unusual steepness going on. And we can do some investigation later about which it is, but that's kind of why we're looking at this. All right, so let's come down now to the second example. We want to show, all right, so this is going to be some justification using calculus, that the slope, key word, and slope basically is key for the derivative. Slope of every line tangent to the curve. So they're going to be talking about the derivative. I'm trying to show that the derivative is positive. Show that the derivative is always positive. All right. So basically, find the derivative. So step 1, find f prime of x. Now, when I go to do that, I am going to rewrite this one. I could use quotient rule, it's fine, but this is 1 over a power composition. So I'm simply going to first rewrite f of x as 1 minus 2x to the negative 3, because that's going to make it easier to do the chain rule. My chain rule, my u would be 1 minus 2x. My du dx is going to be negative 2. That makes me having y equal u to the negative 3. My dy du would be negative 3u to the negative 4. And so for me to find f prime of x, or my dy dx, I take du dx times dy du, and I will have my answer. So we end up with f prime of x is negative 3, and instead of my u, I put my u back in, 1 minus 2x to the negative 4 times my du dx, which is going to be negative 2. Right? And again, because I'm going to use it, now step 2, I'm going to rewrite it in a nice form. Again, one fraction, simplified factored. It's already nicely factored, so I really just pretty much need to go f prime of x. The numbers in the top would give me 6 over 1 minus 2x to the 4th. Okay. So the first thing is we would like to determine the domain. All right. Now notice that this said the slope of every line tangent to the curve. Now that's assuming that the tangent line exists. Now clearly at this point, hopefully you're looking at this derivative and saying, hey, this is clearly going to be a always positive when it is defined, because 6 is a positive number and any number raised to the 4th is positive. So right now I can conclude f prime of x is greater than 0 or positive for all values in its domain, basically because you have a positive number divided by a positive number. Okay, so that's a kind of an obvious thing. You don't really have to do much justification for that. Now, what might be more interesting in this problem is to go ahead and figure out what do we know about the fact that our derivative is always positive. All right, our derivative is always positive means that f of x is going to be increasing for all values in its domain. Now let's kind of talk about this. Now I'm going to kind of come back into both of these examples, kind of relating it to the next kind of application chapter we're going to do. Once we get a lot of this information, kind of one of the things we want to use is be able to kind of sketch a picture of it. So actually, let's come back to this one. We're going to actually do both of these. We're going to sketch pictures of this. Now, let's talk about example 2. So I found the derivative. I know where it has horizontal tangents, so that's going to be possible extrema or point of inflection, some situation like this or like that. And we know where it is, the derivative doesn't exist, so we must either have a cusp or a vertical tangent at plus or minus 1. Now, what I'm going to do is basically kind of extending this into the next section. I'm going to do a sign chart on f of x and its derivative to kind of see what's happening. All right. So on our critical values for our sign chart for our derivative, your f prime of x, when we look at it, it equals 0 when x was 0. So we'll put that on. We'll put the 0 up here. It was undefined at negative 1 and 1. So this was I'll put a u and a u, not differentiable there. Now, in terms of the function increasing or decreasing, what I basically need to do is look at the sign of the derivative. So picking some values, you test. You can take a look. This is a pretty straightforward one. If I pick a number down here, say negative 10, the top of the derivative would be negative. The bottom of the derivative would end up being positive. Negative over positive is negative. The in between, if I pick negative a half, the top would be negative. The bottom, negative a half squared is 1/4. 1/4 minus 1, this would end up being a negative. A negative over a negative is positive. If I put in 1/2, It's going to be positive, but still negative on the bottom, so now I'm negative. And then we have our, say, 10, positive, positive would be positive. Now what you do with this derivative is we're going to make some conclusions about f of x. Now, if the derivative, the slopes are negative, we know that this is decreasing. If the slopes are positive, we're increasing, then decreasing, and then increasing. Even though the derivative is undefined, we know f of x was defined at -1 and 1. So at -1 and 1, because it was defined, we want to basically figure out what's happening here. We could take a look at the limit as x approaches 0 on the left and the right, kind of figure out what's happening to this. But let's think about this. This function is going to basically decrease, increase, then decrease, and then increase. Well, right here, this is going to be an extrema. It's increasing and then decreasing. So that one is going to be a local max. Now here we went from decreasing to increasing, but it was defined there, so this must be a local min, and it's not going to be a local min in the same way here because the derivative is undefined, so it must have a cusp or something going on here. And then the same thing's true over here. It goes from decreasing to increasing, so this would be a local min, but it's a special local min. It's not going to be the nice one with a horizontal tangent line. It's going to have to be a cusp of some sort. So I'll put a little circle on those. Now, one additional thing that we could do, and we're not going to do that here, is maybe take a look at concavity. Concavity is where I would use the second derivative. We won't do that here in the interest of time, but let's take a look at our actual graph of this just to kind of relate it to our derivatives and the information that we have found so far. All right, so I'm going to pause it so you don't have to wait for me to put this in. All right, and so here's the graph of that function. And as you kind of see, you can take a look right here that you have decreasing, increasing, decreasing, increasing, and look, at -1 and 1, where the derivative did not exist, there appears to be a cusp there. While at 0, where you had a horizontal tangent, you have a nice smooth part of the graph where you have an extrema. Okay, again, just kind of previewing some things that are going to come in the next section. All right, let's come down here and look at this one. So on this graph, okay, what we know is that it's always positive. So our function for its domain is always going to be increasing. But maybe we should think about finding the domain. So taking a look at this. All right, so let's figure out what our domain is. Now, first off, we just basically have a division by 0 problem. So f of x, f prime of x, equal to 0, that's going to be a never, right, because of the top of the fraction. Your f prime of x not existing, that's we're going to look at the bottom, 1 minus 2x to the fourth equal to 0, basically 1 minus 2x equals 0, x equals 1/2. So at x equal to 1/2, we're going to have a discontinuity on it. But now let's think about what's the difference between this one and the previous one. F of x, the original function, okay, taking a look at that, was 1 over 1 minus 2x cubed. This is undefined at x equal to 1/2 also. So what we know, which is different than before, the example 2 function f was continuous and defined everywhere. So that's why the derivative being undefined meant we had a cusp in that location. But now the derivative does not exist, but neither did the original function at x equal to 1/2. And that goes back to the if you are not continuous, then you are not differentiable. So what must be happening here? Well, if we think about this function, this is a number divided by 0. If you were to do your limit on f of x, you're going to have that vertical asymptote. So this is going to be a vertical asymptote and infinite discontinuity on the original function, so of course it's not going to be defined on the derivative. All right, and if we take a look at that graph, we're going to do the same thing. I'll pull up the calculator and take a look at this graph to kind of show you what the relationship is. Again, I'm going to pause it so you don't have to watch me enter it in the calculator. And here you can see that we have a function I just graphed f of x. And notice that it's increasing, has a vertical asymptote at 1/2, and then it is increasing again. So our function was increasing the entire time for all values in its domain, and then it had a vertical asymptote at x equal to 1/2. All right, let's take a look at the next example. All right, the next example, we want to find dy dx and then simplify. So this is really just kind of an idea of just practicing straight up using our product rule and a chain rule in this. All right, now I'm going to rewrite this as x squared times 1 minus x squared to the 1/2. Right? So when I go to do dy dx, I'm going to remember that I have to use product rule. I'm essentially determining that this is my f and this is my g. So I need to do f times g prime plus g times f prime. So my f is going to be x squared. My g prime, maybe we'll put parentheses here and we'll come back to that because that's a chain rule problem, plus my g, 1 minus x squared to the 1/2 times f prime 2x. All right, so sometimes I come back in, we'll fill this one in on, by itself because it's a little complicated. For my g prime, maybe over here on the side, I'm going to let u equal 1 minus x squared. Du dx is going to be 2x. And so we're finding the derivative of u to the 1/2, which would be 1/2 u to the negative 1/2. So I kind of do my scratch work. Now I come back over here. I would have 1/2 u, 1 minus x squared, to the negative 1/2 times du dx, which is 2x. So I fill in my chain rule. Now, this is where we're going to start practicing the simplifying. Okay, so you found the derivative. Now what you want to do is simplify. And what you want to recognize is you want to be able to pull out common factors. You have two terms, term 1, term 2. You want to look for factors that you have in common and pull out those factors to the smallest power. That's how factoring works. So in between the two, we definitely have a 2x here, and we have a 2x there. So we're definitely going to pull out a 2x. I also see that I have this factor of 1 minus x squared in both of them. They're to different powers. That doesn't bother me. What I know is I'm going to pull out 1 minus x squared, and I'm going to pull out this GCF of the smaller power. So I have 1/2, negative 1/2. So we're going to pull out negative 1/2. All right. Now when I do that, remembering factoring is really just dividing. So, and when you divide, I'm basically going to take this, I'm going to divide out the 2x, I'm going to divide out this, what's left, x squared over 2. All right. Plus, now over here, when I divide it out, again, I'm going to divide out the 2x, that goes away. When you divide these two, you're like, oh, they have different powers. All you have to remember is you do what to exponents when you divide? You subtract their powers. So I would have my 1 minus x squared. The top power is 1/2. I'm dividing this one out, so I subtract the negative 1/2 from it. And really, this is nothing more than try to keep your negatives straight. So we have a 2x, 1 minus x squared to the negative 1/2, and then within the parentheses, x squared over 2, and this becomes 1/2 plus 1/2, or 1. So plus 1 minus x squared. Now, in terms of simplifying, we are going to do the same thing. We want to put it in a nice form, which is one fraction always factored. So over here, I'm going to actually combine these together, as well as putting this in the denominator of fraction. So I'm going to make it 2x in the top. I'm going to make this the square root of 1 minus x squared. And then here you have half of x squared minus x squared, so that would be negative 1/2, sometimes we'll do on the side, negative 1/2 of x squared plus 1. And we prefer to have it all into a single fraction. Okay, so this is basically going to be 2 over 2, right? So I'll just go 2 over 2, so that I can get it together in a single fraction, which is going to be negative x squared plus 2 over 2. All right. So I'm going to put that over here, negative x squared plus 2 over 2. And then what I like to do is, look, I got some canceling, so that will go away. And then here, I like to have the x squared positive. So I'm going to pull out the negative. I'm going to leave the x, and this is going to become x squared minus 2. And then all over square root of 1 minus x squared. So we're going to do some algebra. All of this part right here is simply algebra 2. Simplifying it down and putting it in a nice form. And one fraction factored form is what we mean by nice form. All right, let's take a look at B. All right, so we want to do this one. Again, the same idea. The example that we had above was a product rule. Now I want to do one with a quotient rule. Okay, I am still going to rewrite this a little bit. I'm going to write it as x over x squared plus 4 to the 1/3. So this is going to be a quotient rule with a chain rule included in it. So here's my f, and then this would be my g. All right, so let's remember that our quotient rule, I'll write it up here, f prime of x, is going to be low d high minus high d low all over low squared. So that's basically what I'm doing. And the ones that are hard, when I go to do the derivative of the low, I'll do that kind of separately. So we have our low d high, that's nice, 1, minus our high d low, I'll put a big parentheses, come back and fill that in, all over the low squared, x squared plus 4 to the 1/3 squared would be to the 2/3. Right? Now here I got to figure out that g prime. So again, because it's chain rule, I might do it over on the side a little bit, do a little side work over here. Basically, I need to have my u. So my u is going to be x squared plus 4. My du dx is going to be 2x. And what I'm trying to take the derivative of is u to the 1/3. So the derivative, I guess I should label this, dy du, is going to be 1/3 u to the negative 2/3. Okay, so I kind of fill in my work for my chain rule. Now I come up here and I do it. So I have 1/3 my u, x squared plus 4, to the negative 2/3 times du dx, 2x. So that gets us to this. That's the taking the derivative. Now we're ready to go to simplifying. And again, factored form one fraction. I already have it in a fraction. Now I'm going to look at the top, and I have two terms, here and here, and I'm going to start looking for things they have in common. The only thing they have in common is this x squared plus 4. And then I choose the lowest power, so that would be the negative 2/3. And that's what we're going to factor out. I'm going to go ahead and just put the fraction bar back in, bring the bottom, and hopefully you kind of preview of coming attractions in the next step. Notice I have a common factor that I can work with outside. But before I do that, I need to figure out what goes inside the parentheses. Remember that you are dividing this out. So when I divide it out, I am going to subtract the exponents, right? So I'm going to end up with x squared plus 4 to the 1/3 minus negative 2/3 minus, and then up here this goes away, and then I have an x, a 2x, and this 1/3 left, so I would have 2x squared over 3. Alright, everybody good with that? Now what's nice about this, and when you do this factoring correctly, 1/3 minus negative 2/3 is actually a power of 1. So I'll just go ahead and make a note of that there so I don't have to kind of do another step to rewrite it all out. So inside these parentheses, if I simplify, I really have x squared plus 4 minus 2x squared over 3. And so let's go ahead and put it in a common denominator, which is going to be a 3, or factor a 3 out. If you think of it like that, 1/3 out. Either way, let's just find a common denominator. Probably be easier for you guys in your number sense. If I multiply this by 3 over 3 to get a common denominator, I would have 3x squared minus 2x squared. And then I would have plus 12. Of course, that's all over 3 because I found a common denominator. And then these two right here, I'm going to simplify that as well and be like, oh, let's take a look at this. This is going to be subtract your exponents. Negative 2/3 minus 2/3 is negative 4/3. So this would end up being times x squared plus 4 to the negative 4/3. And then my last step, just to put it all in a nicer form, we would end up with, in the top, x squared plus 12. In the bottom, the 3, and then this will move to the bottom, and we'll write it in the radical form. So we would have the cube root of x squared plus 4 to the 4th. And then that's our quote-unquote nice form that we're looking for. All right, let's do example 5, and then we'll finish out this set of notes. So example 5, just some chain rule practice with trig functions. And notice this one's playing on the cosine. Make sure you pay attention that you know what's the inside function for each of these. That this is kind of understood here. This means something completely different. This is a number times x squared. Whereas this is the cosine of, and again, even though we don't write it, we understand parentheses to be there. This one is understood to be cosine of 5x squared. This one would be cosine of 5x to the 1/2, whereas this one would be cosine of 5x to the 2/3. So the trick in this example is to simply be able to rewrite them. Now in this first one, u equals 5x squared, du dx equals 10x, and then y would equal cosine of u, and dy du, derivative cosine is negative sine u. So there's my work for doing the chain rule, kind of the scratch work, and then I'll come over here and go, all right, f prime of x is going to equal the negative sine u, 5x squared, times the derivative of the 5x squared, which is 10x. So that's that derivative. Over here, there's no chain rule. This is nothing more than power rule. This is a number times x squared. So we're simply going to do 2 times a times x. So f prime of x, noticing when you have chain rule and when you don't, it's going to be 2 cosine of 5 x. I'll put parentheses in for clarity. Okay, and again here, now this one has a chain rule within a chain rule, but again, this is simple. I'm not going to do chain rule within a chain rule. I'm going to go, that's the same as cosine of 25x squared. Make your life easy when you're doing these. So your u would be 25x squared, du would be 50x, and do I really need to keep doing, hey, y equals cosine of u? I kind of already have it over here, so I'm just going to repeat the process. So my derivative, f prime of x, would be my negative sine u, 25x squared, times du, dx, bad notation there, which is 50x. Done with that problem. Let's take a look at this one. Now this one, because we have chain within a chain, there's really nothing you can do about this. So you kind of have to do this one in 2 steps. Your first u is going to be cosine of 5x. Then du dx is going to use the chain rule itself. So to find this one, you could, if you want to write it down, go v equals 5x, dv dx is going to be 5, and then that would make it cosine of v, and this is u equal to cosine, so du dv would be derivative cosine negative sine v. But notice it has the same pattern. You can almost start skipping. You don't always write these 2 parts down. So I have negative sine of the v, which is 5x, times the derivative of v, which is 5. So I have that. And then over here, we're also trying to take the derivative of y equal to u squared. So we would have dy du is 2u. So my f prime of x, let me change color so I have enough room, f prime of x is going to equal, start over here with the outside, the u squared, so I would have 2u cosine of 5x there. So 2u dy du times du dx, which is negative sine 5x times 5. So we have, be careful with those negatives. I like to put an extra set of parentheses in so that the final version for this, if I write it in a prettier fashion, there's 2 and a 5, so that would be 10. It would be negative, and we would have cosine of 5x and then our sine of 5x for that one, for the nice derivative. Same thing here. Since I've already done this work, I don't have to do it again. So I'm just going to come straight to the derivative and say f prime of x. This is u to the 1/2. So the derivative would be 1/2 u to the negative 1/2 times the derivative of u with respect to x, which is going to be that negative 5 sine of 5x. So there's that derivative. And then our last one here, same thing. I don't have to repeat the process. I'm still using that u. So my f prime of x, this is u to the 2/3. So it would be 2/3 u to the negative 1/3 times du dx, which is our negative 5 sine of 5x. All right, so we'll stop that video there and pick up with example 6 in the next one.